Hello and welcome to episode number 21 of CS350 Online. I'm your host, as always, Leslie Eisted, and on today's episode, we are going to continue our discussion of file systems, focusing today on the virtual file system and the physical file system. But of course, first we have to talk about our OS of the day. So today, it's Linux Day. We finally made it there. And you'll note that we're pretty much at the end of the course before we get to Linux, because Linux is actually a fairly new operating system. So in 1991, an individual by the name of Linus Torvalds decided that he wanted to make his own operating system. Now, it wasn't that he necessarily wanted to make his own operating system. It's just he wanted a fully functional, free operating system. And at that point in time, there simply didn't exist any. And while there were projects underway that would have suited his needs, and he has said that had those projects been available, he wouldn't have gone out and made Linux. They simply weren't available. So Richard Stallman was working on something called the GNU project, but its kernel was stalled, there was no release date, various complications. 386 BSD had a lot of legal complications. It happens. So because these projects weren't ready, he actually went out and created the Linux kernel. And he tried to incorporate as much of the GNU project's software, which was free, of course, under GPL'd, into Linux's kernel and the operating system as a whole. And it said that it was originally called FreeX. I'm not sure how you're supposed to say that. FreeX. And that he didn't originally want to name the operating system after himself, but it was after much discussion online that he finally did rename it to Linux. Now, I want to say, what is Linux? Well, most of you know, because if you've been doing the assignments in this course, you've been using it. You know that Linux is a Unix-like operating system. It has a monolithic kernel. That is, everything in the kitchen sink is in it. Now, that's not to say there aren't versions of the Linux kernel that aren't microkernel, but by default, it's monolithic. And that means, so we've got memory management, it's got virtual memory, IPC, scheduling, file systems, device drivers, which comprise probably the biggest block of code in Linux right now. They are all in the kernel. Now, one of the things that's interesting is that X Windows itself is not actually part of the kernel. So your desktop environment, which is much more integrated into the operating system with something like Mac OS or Windows, in Linux, it's not so integrated into the kernel. And you are actually free as a user to use whatever kind of desktop environment that you want. Now, personally, I prefer to use KDE, and I've been using KDE for a very long time. 20 years, 15 years, 20 years, a long time. But there are, of course, others like Unity. There was GNOME, which I think is now Unity. There have been many. You could use TWM, which is the window manager, and it's very bland and boring, but it's your choice, and that's kind of neat. Now, one of the fun things about Linux is because it is an open source project, anybody can start writing code for it. So if you want to create your own distribution of Linux, you can just download the source code and make whatever modifications you want. And as a result, there are numerous different distributions of it and software packages. And it's even the basis for Android. And Google keeps saying someday we'll merge it back into the Linux mainline, but someday doesn't always come. So just to show you some of the different desktop environments that you might encounter with Linux, if you haven't seen them, go here, and I'll come back to that one in a minute. So this is Enlightenment with a black and white theme. Just kind of a cool one. I have a really good friend who's a big fan of Enlightenment. This is a really old version of KDE. And I could show you, TWM, but you'd be horrified by it. So what I do want to do before moving on is show you this kind of diagram of the Linux operating system, Linux kernel, whatever you want to call it. So in black down here, you have the hardware. That's the actual bare metal, as they like to say. And in red, you've got the things that are running with kernel privilege. So that's device drivers, any kind of kernel modules. You've got things in here. You'll see some bus stuff. You've got some networking things in here, some graphics card drivers, which is very important, ALSA, your sound, and so on. And similarly, in the Android kernel, which is, again, just a fork of the Linux kernel, we've got similar concepts. And then there's a layer that sits kind of on top of the Linux kernel. And it's not running with kernel privilege. But I want to say it's not something the user is going to be directly interacting with. Now, a developer would, but not a user. This is where your X servers are going to be. So things like X11R6, which nobody uses. Or you've got Xorg, X386. This is where you've got glib, cliving, and all of those different libraries, and so on. And then on top of that, we have more user-friendly libraries, so things like GTK Plus and Qt, which are windowing libraries, FLTK, and WX widgets. And so those are more of a high-level libraries. And then finally, on top of that, you'll see also even more higher-level applications. So Linux has a lot of different layers to it. Just kind of a neat model. Oh, yes, and it wouldn't be complete without somebody trolling with the new Linux stuff. Look, I've been using Linux since about 96, 97. I know it's just the Linux kernel. Too bad. I can't even pronounce that word. All right. Sorry, that was comments on Twitch for anyone who's a little lost. All right, so where did we leave off last week? So in our last episode, we finished discussion of the logical file system. So let's go up here into our file system slides. And we had discussed what a logical file system is. Now remember that our logical file system is going to be the high-level API that's actually presented to the user. And this comes in two kind of different ways. This is how, when you are writing a C++ program or a C program and you want to read or write to a file, it's the logical file system that is presenting you commands like open and write. And those are, of course, system calls. But you don't, when you are writing to a file and you're writing the code to write to a file, you don't have to do anything about what physical file system's underneath, what particular SharePoint it's on. You don't need to worry about that. You just open the file, you write to it, and you close it. And magically it gets stored correctly, and that magic happens in the back end in the kernel. So the logical file system is that really high-level abstraction. And you also experience this when you are opening up like File Explorer or any, whatever it's called in Apple here, Finder, I guess, and then Dolphin and like KDE. When you open that up and you're like searching through directories, you're making use of the logical file system. So a couple things just to remember. When you open a file, there's actually quite a few things that happen. It's not just getting you this unique file identifier. It's letting the process know and that, hey, you have this file open now. And the process is actually going to keep track of the fact that it has that file open in what's known as a file descriptor table, which is a part of the process's structure. And the file descriptor table will keep track of what kinds of permissions we have, and it also keeps track of our current position in the file. And then we are also going to tell the kernel that we have another process with this file open. And then what's going to end up happening is when you close the file, so when you open the file, the kernel increments the counter, and when you close it, it decrements. And when the counter is 0, there's no point in keeping it in the kernel's open file table anymore. So lots of business happens there. And similarly, things are going to happen in close. Read and write are interesting because the reads and writes happen sequentially. That is, from your current position in the file, we are going to read some number of blocks or bytes of data. And it only ever happens sequentially. So if you read 512 bytes from the beginning of the file, well, then your file pointer is at byte 512, and your next read will happen from there. If you want to do random I/O, you're going to need to use the seek operation. And then, of course, we have all of these different metadata commands, which we explored a little bit last day. And then we talked about directories and what they actually do. We mentioned that each file in your file system actually has a unique identifying number known as the I number. And that internally, your computer much prefers to refer to the file by its number rather than its name. And that makes sense, because who wants to do all that string comparison bullshit? You want to just do some numbers in the back end. We do want our OS to be fairly fast. So we need some way then of actually mapping the name of the file to these numbers. And so that we can actually find, given a string path, I want to be able to find the number. And that's actually what the directories are for. So a directory contains the mapping between the name of the file and the unique I number. And we call that a hard link. And then when you open a file, what's interesting is you're going to be actually you're going to be traversing this namespace tree, and you're going to be looking at each component of the path and looking it up in the directory to find the I number so that you can open that file up and then continue your search. One of the things we ended discussing was the fact that you're not allowed to have multiple hard links to a directory. So we do permit multiple hard links to the file. So the file 147 here is known as foo.my, but it's also known as docs.a.txt. And but you can't do that with a directory. And it's the reason is they don't want to have cycles in directories. And it's not that every hard link would necessarily cause a cycle, but they simply don't want to have to do cycle detection. It's not to say there aren't any logical file systems that don't permit it. It's just we're going to say that they're not permitted for simplicity's sake. All right. So with that, the next file system that we need to look at is the virtual file system. And this is where we take multiple physical file systems, and we're going to present them up to the user as one unified thing. So the user is not really aware that there are two different devices. We just see and treat them as if it was a singular device. And how this happens really depends on the operating system. But there's two that I like to show. So the first one is Windows. And I'm actually going to switch over to OneNote here to show you Windows. So if you've ever had a Windows computer, one of the things that you might have noticed is that the name of every file looks like this: C:// and then you'll have something like that. And your files are all going to be prepended with this C:/. Well, as it turns out, how Windows supports joining multiple file systems together is by having a two-part name. So you can see the two parts here. The first part, which I've circled in blue really badly, this is actually the file system identifier. And then in red, what we have is the actual path to the file. Now, and so what's going to happen is when you want to access a file on drive C, you do C:/downloads blah.mp4. And if you want to access something on the network, it would be N or Z:/downloads blah.mp4, whatever it is. They've separated it into two parts, and because people have been using this for so many years, it feels very natural. Although one thing people often wonder is, Why did we start at the letter C? I can explain why we started at the letter C. My very first computer was a 1981 IBM PC. That's the first personal computer that was released by IBM for home users. And by default, this computer didn't come with a hard drive. At the time, you either had 2 disk drives or you had a lot of self-booting disks. So you didn't actually need a hard drive. And because those early machines didn't have a hard drive and they were using a Windows-like fat file system, they chose to do, in DOS, your first floppy drive was A. And if you had a second floppy drive, it would be, of course, B. And since everybody had these letters, when hard drives started becoming more popular, people had gotten accustomed to the fact that floppy was A and B. So they figured, well, the hard drive will then just tag it on as C. Now, floppy drives persisted in desktop machines, I want to say through till the early 2000s, and so this still made sense. Now, nobody had a B drive because why would you have 2 floppy drives in your desktop in the year 2000? But you still had a 3.5-inch floppy A drive. Now, of course, nobody has a floppy drive anymore. Most people haven't even seen one. And we're left with these 2 letters, A and B, seemingly not used, and we're starting our letters at C. But that's actually wise because of floppy disks being a little bit more common earlier on than actually having a hard drive in a consumer-level machine. Fun story. I actually did eventually get a hard drive for that machine, by the way. It was 5 megabytes, and it was about that big. It was huge. I took it out of my friend's XT. But she didn't want it anymore. Okay, admittedly, the XT was probably 15 years old when I took it. All right. So that's how DOS Windows does it. And so we've been doing that since about the early 80s. So it's fairly common. Linux and Unix operating systems, they actually do this very differently. So how they do things is by... they call it mounting, and the idea is you're temporarily combining the 2 namespace trees. So what this actually does is, and we have this warning here that says mounting does not make 2 file systems into one, because this is a temporary join. So what you've got here on the screen is you've got the root file system, your host file system, and you've got the file system on your USB drive you're about to plug in. So you plug it in, and for some reason it doesn't automatically mount, and so you manually tell it, mount file system X to point XA. And what you are doing is you are going to take that namespace tree for file system X and you are going to attach it temporarily to XA. So now you can actually access everything in file system X by prepending it with XA. So if you're looking for the file G on file system X, which is at path XG, then once you've mounted file system X, you can find it by going to XAXG. Now, one of the interesting things that you're going to have happen here is that these 2 file systems didn't exist knowing each other. And so it's entirely plausible that XG's I number and YK's I number are actually the same. But remember, we haven't actually combined the file systems. So we don't have duplicate entries. And the operating system is actually going to, the kernel that is going to keep track of what's going on internally. And it's going to keep track that, oh, this I number actually corresponds to this device. And this other I number corresponds to this other device. So even though it looks like we may have some duplicates, the kernel is able to keep these separate. And of course, since the user doesn't use the I numbers, they'll never know. So that's really all there is to say about the virtual file system. It's not terribly exciting. What I want to do now then is actually talk about the physical file system. But before we do that, I'd like to introduce you to first sample problems. So we have a question, by the way, here. How does something like a USB reconcile the two methods of merging file systems? So I'm going to presume you're referring to how do we have something like a FAT-based file system join up with an ext4, a Unix-style file system. So this is going to have, the kernel is going to have a driver for that file system. So for example, things like Apple don't really support things like NTFS very well. But the kernel is going to have drivers for that file system. It's going to need to know how to read that file system so that it can retrieve its namespace tree. And then what will happen is, you may have noticed when you plug in something like a FAT formatted drive, which would you typically think of it as like C:/, but that C:/ is really just something that the OS does that's not actually built into the physical file system. So that C:/, it's not the physical file system, that's the OS that does that, first off. But secondly, to combine these different things together, on Windows versus Linux, of course, they first have to have the driver to understand how to talk to that file system. And then secondly, they'll just use their native method for combining those two together and presenting them as one. But yeah, no, that C:/ or the mount part isn't a part of the actual device. That's how the kernel combines them for the user. So it's not on the physical devices. And if you want to think about it another way, if you have a USB device and you plug it in Windows, on one Windows machine, you may get assigned drive letter D. You can plug it into another computer that's got 20 things plugged into it, and you might get assigned drive letter N. So that just goes to show you that that method of either having a two-part file name or using the mount point, that is not actually part of the physical disk. That's actually the kernel that's doing that. All right. So then we have to talk about, I said I had a sample problem. So let's bring up a sample problem here. If you heard a cute little voice, that was my son cooing. Don't worry, he's not by himself. All right, so this sample problem here you can find in our sample problem book. This is called path trans. And what we've got is a problem where we want you to be able to take a path, and using these functions that we've provided with you, we want you to retrieve the I number for a file, or retrieve an error code if the file doesn't exist. So this is path trans, and we're not going to take this up today. We will take this up in our next episode. All right. So then, let's now move on to talking about the physical file system. So first off, when we're talking about the physical file system, we need to ask ourselves, what information do we actually need to save permanently? That is, what do we need to persist without power? And the obvious things are the files and the metadata for the files. But there's actually more information than that needs to persist. For example, directories and links, because how are you going to retrieve those files after the fact if you don't have a means of doing some kind of lookup? So anything to do with searching or looking up a path name and getting the file, that's going to need to persist. We're also going to need to have persist any information about the physical file system itself. For example, the FAT file system or the NTFS file system. They are different from each other, and how they are laid out on the disk is different. The kinds of metadata to describe the file system itself is different. That information needs to persist because when the kernel of the operating system boots and it wants to access one of these drives, it needs to know how to interface with that specific device. So information about how the data is stored on that device needs to persist as well. But there's a lot of things that we actually don't need to persist. So things like the file descriptor table for a process. That doesn't need to persist, because if we shut our computer off, the computer is off, it's dead, your process is gone, so we don't need to keep it. Things like which files and how many processes have those files open inside of the kernel, we don't need that either. And then any cached data, we don't want that either. Now, I want to say that this second point is rapidly changing, because obviously we want to give users the best experience as possible, which means when they fire the computer back up, it would be really nice if Chrome opened back up at the exact position where it left off. I know I like that, because I always have like 20 tabs open and I'll forget if I don't know what they are. I won't be able to reopen them. So some operating systems are offering various levels of support in the sense of storing process state a bit more persistently. And that can include file positions. And that's including for things across, not like sleep, but more of a hibernate and even power off, but also things like cached copies of persistent data. So when you're loading a file from the disk, because you know now how slow reading from disk is, we obviously keep some kind of cache in memory so that we don't have to go to disk as many times. This here, we're actually now using, that's what the 3DX point, the Intel Optane is it is actually a persistent cache for data blocks from physical file systems. So things are changing. They're always changing. We're going to keep things simple, and we're going to say only these things need to persist. So to show you how, or to give you an example of one physical file system, we're going to create a disk. The disk stores 256 kilobytes, and it's going to be a mechanical drive. Sorry, I got to sneeze. Trying not to sneeze. We have our disk with many sectors. Each of those sectors will be a standard 512 bytes. Now, to eliminate or to reduce the total number of I/O operations we have, we're going to actually group consecutive sectors, so into 8, and that's going to be a block. So every 8 consecutive sectors forms a block. And our file system isn't going to do sector reads and writes. Our file system will actually do block-based reads and writes. And we will also do block-based addressing. Now this actually, even though the disk does sector reads and writes and sector-based addressing, this works out because the block is a bunch of consecutive sectors. So there's no worries there. So this means that our blocks are 4 kilobytes. That's convenient if we're doing on-demand paging, because each page of the address space would be one I/O operation. And my lovely 256 kilobyte disk is going to have a total of 64 of these blocks. Now, why did we choose such a tiny disk? So we could draw it on the slide. And you could actually, count it reasonably. So this is the way that we're going to divide up our disk. You'll note that we've actually subdivided the disk into the 64 blocks. Of those 64 blocks, we are going to reserve 8 of them to be used for something special. And that leaves the remaining 56 data blocks to be used for actual user data. Now, a couple things about our file system. Data blocks cannot be shared between 2 files. So if a file uses only a single byte, technically speaking on disk, it's going to occupy the entire block. So if you've ever, this is one of the many reasons why the file size on disk versus the file size are different, is because we can't share data blocks, number one, but number two, as we're going to see, some files actually have a bunch of other data stored in order to actually keep track of where the file is. So we have 56 data blocks, which means at maximum, we can store 56 non-empty files. Now, the data blocks aren't that interesting, so what we really want to look at is those first 8 blocks. Those are going to be the information about the file system. So first off, so we've got 0, 1, 2. So blocks 3 to 7, so there's 5 blocks total at the beginning of the file system are going to be reserved for what's known as the inodes. So every file in our very simple file system has what's known as an inode. And our inode is going to contain all of the metadata for a single file, just one file. It's also going to keep track of where the contents of the file can actually be found on the disk. Because remember, while for a hard drive, sequential I/O is more efficient, that also leads to a fragmentation problem. So we're going to actually scatter the file to the wind, like paging. So we need to keep track of that. And that's what our inode is for. So we're going to reserve 20 kilobytes of this disk to store our inodes for the files. We'll look at inodes in a little greater detail in a minute. Now, in our system, each of our inodes is 256 bytes, which is woefully small. And yet, as you're going to see, it's actually more than sufficient to support files that are like 4 terabytes in size. Don't worry, we will do some math to show you exactly why that works. So that means that we can actually store 80 inodes, which means the maximum number of files that this disk can actually support is 80. Now, you'll note that the maximum number of files that we can support is 80, but the total number of data blocks we have is 56. And I said very clearly on the previous slide that the maximum number of non-empty files was 56. But you can have an empty file. So the maximum number of files we can actually support is 80. Now, these inodes are stored in an array. And for easy access, we want to be able to get the inode to a file in constant time. So we want to know the index of a file's inode. So you want to know that I number, you want to know where it comes from? Well, that I number is actually the index of that file's inode in the inode array. It's that simple. Because now that we know that this is file, 56, all I have to do is do a direct read from block that has array index 56. I don't have to read in the inode array and search because I know exactly where in memory it is. So those I numbers are very, very useful. Okay. Now, here's the thing. When you create a file, you need to find an inode slot that's available. You could read in each of the blocks of the inode array, and you could check to see is this one in use, is this one in use, until you find one that's not in use. And for this tiny disk here in this silly file system, that would be okay. But that doesn't really scale well, because if you think about it, and I want to point behind me and like, oh, my NAS is here, except my NASs aren't there anymore. They're downstairs in my server room. I have a NAS, that's a network attached storage, and it has 4 14 terabyte drives in it. Okay. How many inodes do you think are in that file system's inode array? Do you think the inode array for that could be a couple gigabytes in size? Because I bet it is. Here's the thing. If I'm trying to find a free inode to create a file, do I want to read in linearly gigabytes of data to search? No, I want to do something faster. So 2 blocks are reserved for what's known as bitmaps. So the inode bitmap, which is the I here, is an entire block on this disk. And each bit of the inode bitmap corresponds to 1 inode. If the bit is 0, the inode is free. And if the bit is 1, the inode is in use. So I still have to read something in from the disk, but I have to read significantly less. So it's a little bit faster. Now, you might be wondering, well, this 1 bit, is that enough? Well, because 1 block is 4 kilobytes, that means there are over 32,000 bits in that 1 block, which means I could, with 1 4 kilobyte block, track over 32,000 files. But I only have 80 inodes, so this is more than sufficient. Now, how are we going to know when to stop searching the inode array? Well, that's going to be a part of the file system's metadata that we'll talk about in a minute. Now, similarly to finding a free inode and using this inode bitmap to keep track of which ones are and are not in use, when we actually start writing data to a file, we need to find data blocks in which to store it. Now, you don't want to have to read in 4 times 14 terabytes of data to find a free block. That's ridiculous. Believe me, trying to do a backup of that NAS to the other NAS, oh, that takes a long time. I think it's like days. It's ridiculous. So I don't want to have to search all of that data just to find a free block. So we're going to do the exact same thing to keep track of which of our data blocks are free and which are in use. We'll have a bitmap where each bit corresponds to one of the blocks. And when we need to get a data block to add to our file, we will simply search the bitmap. The first 0, we'll grab that one. Done. Now, again, on this disk, we only need 1 block for the inode bitmap and 1 node for the data block bitmap, which leaves block 0, which we also call the super block. And the super block is actually where we store all of the information about the file system itself. So this is how many inodes do we support? How many data blocks are there? What is the size of the data blocks? What is the address on the disk of where the inode array or table begins? Where can I find the inode bitmap? How big is it? Where can I find the data node block bitmap? Where does it begin? All of that information that we need in order to access this disk are going to be stored in the super block. So just to zoom in here a little bit, you can see that the first 8 blocks of very simple file system, we've got our super block, which is the file system metadata. We've got the inode bitmap, the data node bitmap, and then we've got 5 blocks that store the actual inode array. And the index of your inode in that array is going to be your inumber. So that's it. So let's take a little bit of a deeper dive then on what some of these things actually are and how they're used. So first off, the inodes themselves. I said before that this is a 256 byte thing, and it actually stores the metadata for the file. And you'd be surprised at what we can store in that. So we're storing things like the file type. We're storing permissions. Is this a read-only? Is this a read-write? Groups, owners, all kinds of things like that. We're going to store the file length. Now, the file length is going to be the actual number of file data bytes. As we're going to see, file size on disk and actual number of bytes to the file's data are different. So we're going to store in the inode the length of the data. Then we keep track of how many file blocks are in use by the actual file. And keep in mind that then if we are using 10 blocks, that's 40 kilobytes, we may actually only be using 38 kilobytes of it. That's why we have to keep 2 separate values. Then we're going to keep track of the last time the file was accessed. We're also going to keep track of the last time there was an update to either the inode, or the actual file itself. And if you're sitting in front of a Windows or a Linux or a Mac, you can look at this information because when you look at file info, it tells you about permissions. And it will tell you about things like when was the last time the file was accessed, when was the last time the file was written. It's important information. I always do I like to sort by last modified date because I like to keep track of what I'm doing recently. We're also going to keep track of the number of hard links to the file because that's how we're actually going to keep track of when can we delete the file. So long as there's at least 1 hard link to the file, then the file can be kept. If there's no hard links, nobody can access you because there's no mapping between your path and your inumber, so it's deletion time. Then the last bit of the inode is actually reserved for the purposes of keeping track of all the data blocks. Now, we obviously in 256 bytes can't fit a whole page table. So we have these weird pointers. So first we have direct data block pointers. And I'm going to switch over to this lovely diagram here. And what you'll see here is in this diagram, we have the inode has a number of direct pointers. It's these guys right here. Let's see there. The direct pointers are pointers directly to file data. And we always use the direct pointers to point to the earliest bytes of the file. So when we start writing at byte 0 of the file, we're going to make use of the direct pointers to do that. Now, let's suppose that doesn't give you enough space, because it's not going to give you enough space. Then we have what's known as a single indirect, which means that the inode contains a pointer to a block of pointers, and each of those pointers points to file data. Now we're talking. And if that's still not enough space for you, we have the double indirect, which is a pointer to a block of pointers, and each of those pointers is a pointer to a block of pointers, and those pointers point to file data. And if that's not enough for you, then we have the triple indirect, which is a pointer to a block of pointers, to a block of pointers, to a block of pointers, to file data. And if that wasn't enough, then we could redesign our inode to have quadruple indirect and so on and so forth. But you would be surprised at how much data we can actually access via what we have just here. So let's actually compute it. So if we look at this calculation, and you can find all of the formulas for doing this calculation on Piazza in the extra guide thread. It's already posted. So each of our disk blocks is 4 kilobytes. So if we have 12 direct pointers, then we have accessible via the direct pointers only 12 times the block size. So taking this over here, so accessible via the direct pointers is the number of pointers multiplied by the block size. So in our case, this is, we have 12 pointers times 4 kilobytes. So from direct, we can access 48 kilobytes of data. So I can store an image from my very first digital camera. Yeah, no thanks. My new camera, it's like 10 years old, has a lot more data than that. So obviously we want to be able to store more than 48 kilobytes. So how do we compute how much data we can access by a single indirect? Sorry, looking for a baby wipe here. My son has spilled sticky juice all over my tablet. All right, before we can compute how much memory we can access by a single indirect pointer, we need to know how many pointers actually fit in a block, that is a data block. So, number of pointers in a block is equal to our block size divided by our pointer size. Now, we haven't actually specified the pointer size, but you can always assume if we haven't specified it, it's 4 bytes. So this here, we have 4 kilobytes, which is 2 to the 12, and our block size, or our pointer size, is 4 bytes, so that's going to be 2 to the 2. So we can fit 2 to the power of 10, for a very simple file system, pointers in a block. And now we can compute how much memory is accessible from the single indirect. So it's going to be number of the single pointers in the inode multiplied by the number of pointers in the block multiplied by the block size. Which in our inode, we have 1 single indirect pointer. And that points to a block of 2 to the power of 10 pointers, which each point to 4 kilobytes. So this is actually 2 to the power of 22 bytes. So if you go back on the slide there, it will tell you that that is roughly about 4 megabytes or so. Okay. But that's still not enough. Let's just do all this math over here in OneNote, because it's more fun to do it in OneNote. All right, so I want more than 4 megabytes. I can't think of the last thing I downloaded that was 4 megabytes. What do I want? I want to go into BitTorrent and download something. Okay, let's go into BitTorrent and let's download a copy of every distribution of GNU Linux there is. Every one. That's got to be terabytes. All right, so direct pointers won't cut it. Single and direct pointers don't add enough data. So let's try the doubles. To calculate the amount of memory you can access from the doubles alone, it's the number of sorry, question on Twitter asking, is my NAS for being a Linux seed box? No, it's my research storage. Research storage, backup, security camera feed, you know, all that fun stuff. All right, so doubles. We're going to have the number of double pointers, and that's in the inode, again, multiplied by the number of pointers in a block squared. Because with double indirect, it's a pointer to a block of pointers to a block of pointers to file data. So there's 2. And we multiply that by file size, or the block size. So in our inode, we have 1 pointer, and that points to 2 to the 10 pointers. But since it's double indirect, we square it, and we multiply that by the block size, which is 2 to the 12. So you're going to get 2 to the 20 times 2 to the 12. So that gives you 2 to the 32. Hey, that's 4 gigabytes. So now I can have a 4 gigabyte file, but I don't know if you've ever tried to like download an operating system recently, or like download like an image that actually has everything on it so you don't have to like get all your packages from like a network, but it's bigger than 4 gigs. So this file size isn't going to cut it, and that's why we have the triple. So you probably see the pattern now, but for triple, it's the number of triple pointers in the I block multiplied by the number of pointers per block cubed. Pointer to pointers to pointers to pointers to file, multiplied by your block size. So our inode has 1 triple indirect pointer, and that points to that lovely number there, multiplied by the block size. So that gives me 2 to the 30 times 2 to the 12. We end up with 2 to the 42. Which means that we actually end up, from our triple indirect, supporting up to a 4 terabyte file. Now, this doesn't give us the total file size, because the total file size is actually the sum of all of these. So it's the sum of the direct plus the single plus the doubles plus the triple. So our inode, that is 256 bytes, is capable of storing a file up to just over 4 terabytes. It's pretty good, right? Pretty good. I don't think I have any 4 terabyte files. Pretty sure I don't have any 4 terabyte files. I had to think about that. I have some raw format videos. They can be really big. All right. So, one of the things I'd like to go back and show you is, now that you know how much space this can give us for our file, I want to point out that that's how much actual file data we can store. So our file size is going to be over 4 terabytes, but the file size on disk is actually going to be much, much larger, because each of these blocks of pointers, each of these, this block of pointers, this block of pointers, those are all blocks, data blocks on disk. They don't contain any file data, but they're still on disk. So the actual total size of a file on disk is the inode plus the actual file data plus all of these blocks of pointers. So if you're looking for a little challenge before the final assessment in early August, some calculations I would recommend you try, because there's going to be a lot more calculations on that final assessment, is looking at, can you, given a inode, calculate how much memory is accessible by direct, single, double, triple? Can you compute the total file size? Can you also calculate how many data blocks are being used to store the pointers? I.e., can you calculate this maximum file size, but can you also calculate the maximum file size on disk? So there's lots of fun calculations that you can actually do there. All right, so now you have an idea of how we actually keep track of where the file is stored on disk. Now we should take a look at all of the different I/O operations that happen to read, write, and open files. So let's do that. So let's start with, I want to read from the file foo bar. So I'm going to call open foo bar. Okay. I haven't done the path name lookup. So the first thing I need to do is I need to find the I number for foo bar. So that's what I'm going to do in open. I start at the root, and this is going to be related to the previous sample problem that we'll take up at the beginning of our next episode. But we're going to open the root inode. And we already know the address of the root inode. That's one of those parts of the file system metadata we keep track of where the root inode is. Usually it's 2. So we are going to open the roots inode. And we open the roots inode because we need to get the address of the roots data, because I need to open roots directory and find a mapping from foo to foo's I number. Now, when we open roots inode, it's very simple to think, oh, I'm just reading roots inode from a disk. But remember that an inode is only 256 bytes, and our file system only does block-based addressing, and the disk only does sector-based addressing. So when we say we are reading the inode, what we are really saying is that we are reading the block that contains the inode. But that's a mouthful, so we just say we read the inode. But just keep that in mind. So we read the inode. We read roots inode to get the pointer to roots data. We have made the assumption that directories are able to, in our little simple file system, store all of the hard links in a single data block. So after reading roots inode, we're going to read roots data. By reading roots data, we are able to get the I number for foo. And now we can read foo's inode. Reading foo's inode gives us the pointer to foo's data. So then we can read foo's data. And inside foo's data, we will find the hard link for bar. So we now know the I number for bar, and then we're going to read bar's inode. And so to open, just open foo bar, there are 5 disk read operations. You want to know why we use SSDs today? Do you want to know why we have persistent caches in high-end servers? It's because just to open a file that's not even deep in the tree, It took 5 disk IOs. 5. Each of those disk IOs might have taken 10 or 20 milliseconds because they are not stored sequentially on the disk. Think about that. Now, why do we have to read bar's inode? Well, because when we open a file, we may be opening it to read it. We may be opening it to read and write it. We need to make sure that we, the user that is calling open, actually has the correct permissions to do so. So the last thing we do with open is when we're reading bar's inode, we're going to validate our permissions. And if our permissions match, then we are going to update the process's file descriptor table, give it an entry, start its current position out at 0, and then we're also going to add the file to the kernel's list of open files. And if the kernel already noted that the file was open, then of course we are simply going to increment its counter. 5 disk reads to do that. It's a lot of work. All right. What if I want to read foo's data or bar's data now? So I already know bar's inode. Let's assume that we know its number. We can now access it easily. So in order to read from the file, I need to read bar's inode. Now we're making the assumption there's no caches being used right now. If this was in a cache, we wouldn't need a separate IO operation for this. But let's assume that there's no cache for a moment. So when we do a read, remember that read, we don't tell it where to read from. We just say read 512 bytes. It's from the process's file descriptor table that we get the current position in the file. Why do we then need to read the bar's inode? Well, we need to know what pointer we're going to need to access in order to find bar's data. So we're going to read bar's inode, and we'll see you want to read from byte 0. Oh, okay. Then you want direct pointer 0. So we need to read bar's inode to figure out which pointers we're going to need to access to do that read operation. So we read it. Then we can read bar's data, and we're assuming direct here, direct pointer. And then you'll note that before the read is completed, we write bar's inode. Why do we write bar's inode? Because we accessed bar's data. Now, you'll notice that we didn't do that for the directories. We don't keep track of access times for directories, but we do keep track of it for actual files. And then if we do a bunch of other reads, you'll see it's the same business here. We read the inode, we read the data block, we write the inode. Now, this is making the assumption that we did a direct pointer. So we're reading from the beginning of the file. Because you're going to use the directs. When you run out of directs, then you use single. When you run out of single, then you use double, and you only use triple if you have to. So what happens if you want to read from a single and direct? You're going to read the inode to get the pointer to the indirect block of pointers. You will read the block of pointers, and then you will read the file data. So there's going to be an extra read. And if you have to go through a double, there's going to be 2 extra reads. And if you have to go through a triple, you'll do 3 extra reads. It's costly. What if we wanted to create a file? So this is, instead of reading the file, let's suppose now we want to create the file, foobar. So we're going to start, we create. We have to actually open up directory foo because we need to be able to actually insert a link into it to create our file. So we need to get to directory foo. So we start at the root inode, we read it, then we read root's data. Reading root's data gives us the I number for foo, so we read foo's inode, and then I'm going to read foo's data into memory. So now I have the data block for foo loaded into memory. And I've read through it and I found that bar isn't in it, so I need to create bar and add it to foo. So I need an I number for foo, for bar, because I need to create an inode for my new file bar. So I am going to then read the inode bitmap, find a free inode, and take it. So we're going to set it to 1 and write the inode bitmap back. And then I'm going to write to foo's data to map bar to the I number I just got from the inode bitmap. Then I'm going to open bars inode. I'm going to read it. And I need to read it. You remember that we can't do sub-block reads and writes. So if I want to write 256 bytes of a block, I have to load the whole block into memory first. So I'm going to read bars inode into memory. By that I mean I'm going to read the block containing bars inode into memory, and I'm going to write it. I'm going to clear it out, set the permissions, set the pointers to null, and so on and so forth. And then I'm going to, so I've read it, I've written it, and then since I modified directory foo, I'm going to write foo's inode. So looking at this, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 disk IOs minimum just to create file foo bar. You want to know why your disk light's flickering on and off like a madman? That's why. Then to do each write, we actually need to do even more. So I have to, just like with read, where I need to look at the current position in the file and compare that to the pointers in the inode to figure out which pointer I need to use to access the file's data. When I want to write to the file, I need to do the same thing. So I read the bars inode, I discover, hey, I have no data. So this write is going to happen to data blocks I don't own yet, which means I'm going to have to find a free data block. So I read the data bitmap, I take a data block, I write to the data block, and then I'm going to update bars inode to let it know that it now has a data block and the file size has changed and the modified time changed. And each time I write to a new block, I'll have to do that. Now, what's interesting here again is this is making the assumption we are writing to direct blocks. What if I need to use a single indirect? And I'm the first single indirect block. Well, not only do I have to get the block for the file data, but I'll also have to get a second data block for the actual block of pointers. And if you're the first double indirect, then you'll have to get 2 extra blocks. And if you're the first triple indirect, you'll have to get 3 extra blocks. It's a lot of work. It's a lot. Now, you might be wondering, what if I'm just overwriting existing data? This example here is you're writing to a new file. If you were overwriting an existing data block, then we wouldn't need to go to the data bitmap. We would simply read the bar inode, read any indirect blocks we needed, read the file data block in, write the file data block, update the inode. So getting a new data block is only if we need a new data block. Right. Now, there are some more examples of that in the example guide. So I do recommend that you take a look at that because that's one of our favorite things to do is list all of the IO operations that happen under a read or a delete. Speaking of delete, here's a dirty secret. When you just delete a file, you might be thinking, okay, so it goes through and it goes and it clears out all of the data blocks, it marks them all as free, marks the inode as free, sets everything to 0. No, it doesn't. When you delete a file, just a standard delete, it marks the inode as free and it marks the data blocks as free, but it doesn't actually clear any data out. So all of your data that was there before is still there. So if you want to make sure your data is gone, either delete it 7 times, format 7 times. Yeah, it takes 7 times for a mechanical drive. Or do a secure delete, which is going to read and write those blocks over and over, or make sure that they're all zeroed out neatly. Delete is a tricky little bugger. Never sell your computer having only done a quick format. Because all quick format does is it marks the inode bitmap as free, all of them, and it marks the data block bitmap as free. It doesn't actually touch your data at all. Your data is still all there. Never do a quick format. All right, so you've seen this inode-based file system. Are there any other file systems? Of course, there's lots of other file systems. So that file system you just saw there was very similar to something like ext1 or ext2. Old-fashioned inode Unix file system, and we still use a lot of those concepts today. That's the Unix side of the world. What's Windows doing? Wow. let me tell you about the FAT file system. Well, what it's based on. So the FAT file system, also known as the File Allocation Table file system, is based on a concept known as chaining. And the idea of chaining is, let's store our file as a linked list. So our inode contains a pointer, a single pointer, to the first block of file data. And that block of file data, the last 4 bytes of it, will be a pointer to the next block of file data. And if you're sitting there thinking, but doesn't that mean that if I want to access byte 503 million, that I actually have to read 502 million bytes first? Yeah, it does. So chaining stores your file as a linked list, which means that random I/O for chaining is terrible, but sequential I/O is pretty great. One of the other advantages of chaining is that it doesn't take up so much extra space on disk. It's actually really, really efficient in that sense. Because each data block will only have about 4 bytes used to keep track of where the next block is. Whereas if you look at the other file system there with inodes, we actually end up with all of these blocks of pointers where we may actually only be using 1 or 2 of them. So you end up with lots of extra data hanging around. Okay, there's also something called external chaining. So one of the problems with chaining is that straight up chaining is that in order to access the file, you actually have to load every block of the file into memory. So if we are trying to access, let's say, this orange file here, we're going to start here, and then we'll read this block, and then this block, and then this block finally. But in order to actually get to the end of the file, I actually have to physically read in every block of file data. So if the file was 4 gigabytes, then I actually have to read in all 4 gigabytes in order to get to the last byte. That's a pain. So very, very slow. So external chaining wanted to improve the speed of this. So instead of you having to actually read the file itself, they wanted you to be able to follow the chain without having to read the file data. So they made the chain of pointers external to the file. So they have in the file access table, that's where they're going to store the chain. And essentially, so all of these things, so this entry here would simply be like, this is file X, here's the pointer. And it would tell you where on the disk that pointer could be, and it also tells you the index of the next location of your chain. So we're going to take all of that pointer chain and store it externally. And the idea is you can now get to the last byte of your file or find its index, not by having to read in the whole file, but by just getting the chain, which is much smaller, and then following that chain. Then you get the final block address and you read in just that block. The FAT file system uses external chaining. And by the way, FAT file system is probably, FAT32 is the most supported file system on the planet. It has a restriction of 4 gigabytes, so that's the maximum file size. And whenever you buy like a memory device, like a little flash card or a USB, if it's like 32 gigs or less, or 64 gigs or less, it's actually quite standard for the default physical file system on that to be FAT32. So if you're thinking that you're going to plug it into Windows and copy a 20 gigabyte file to it, it's probably not going to work. I found that out the hard way, by the way. This file system is very easy to work with, which is why it is so well supported, by the way, as well. If you want to maintain a FAT compatible file system, but you want to support larger files, then the file system you're looking for is called exFAT. It's extended FAT, and it can support significantly larger files. But support for exFAT isn't as good as FAT32. So that's chaining. It's a linked list. All right. Now we just showed you that as a comparison, so you could see what are the pros and cons of the inode style, the VSFS versus chaining. And I mean, if we were to just discuss it very briefly here, random I/O with chaining is terrible. But with Unix's, with very simple file system, that inode system, random I/O is no more expensive than sequential I/O. Whereas chaining is really good at sequential I/O. the inode-based file system is going to have larger files on disk than the FAT or chaining file system, because we are going to be storing a lot of extra data to actually keep track of all the pointers. And some of it's going to be empty because we can't do block sharing. So there are pros and cons to each, of course. Now, kind of to round out this module on file systems, we should talk a little bit about file system design. How do people make these decisions to create file systems? Well, file systems are usually designed by thinking about what are you going to use it for. So for example, if I am going to create a file system for a database computer where each record is a kilobyte or less, and I've got billions of them, then I'm going to need a very large inode array. But my inodes can be smaller and my data blocks can be smaller because I know that each file is going to be 1 kilobyte or less. So if I had a 4 kilobyte block, then I'd be wasting 75% of my disk. So instead, if I made my blocks 1 kilobyte, I would significantly reduce the waste. And I could get more files. So I need a really large inode array, small inodes, small data blocks. Whereas if I was trying to archive films, then I know that my minimum file size is like 4 gigabytes. So I would want a smaller inode array because there's less files, and I want larger data blocks so that I would have less wasted space. So whenever you're creating a file system, you have to think about what is the use case. Now there's some statistics given on the slide about, on average we have over 100,000 files. These slides were, this text was written a long time ago. This is massively out of date. Data size is growing, average file size is growing rapidly because people have like 56 megapixel cameras. So of course file size is growing. Nobody wants to download a real media version of South Park anymore. People want to get the 4K version. Or maybe that's just me. All right. So the last thing to talk about, I do want to finish this section off here, is problems caused by failures. So think about what would happen if while you were deleting a file, your power went out because you live at Icon or something like that. So when you delete a file, you have to mark the data blocks as free, and you have to mark the inode as free. So what happens if you mark the inode as free and then the power goes out before you've marked the data blocks as free? When you turn the computer back on, those data blocks are now no longer referenced by any file, but they are also in use forever. So your file system is now corrupted and 4 terabytes of your disk are now gone that you can't get back. So, and there's all kinds of unique, if the power goes off here, then this happens. And this can actually corrupt your file system. And what we want is to make sure that our system is crash consistent. So I want to make sure that the metadata that is actually stored about the file system on the disk is consistent between crashes, because I don't want to lose space, I don't want to lose inodes, and so on and so forth. And the file systems, as we've presented them, are not crash consistent. And I want to say I don't know any that are perfect in this regard. But this is actually, like, when I was growing up, power outages were common. I grew up in the country. We had crappy power, so power outages happened all the time. I had to run programs like ScanDisk and fseek in order to actually, what those programs did was after a crash, they would go through and they would check to make sure that every data block was referenced by an inode. They would make sure that there were, just make sure all of those structures actually mapped out, and they would correct it as best they could. But unfortunately, some crashes simply couldn't be repaired. And periodically, I want to say once a year, once every 6 months, you had to reformat your disk, simply because there were so many inconsistencies in the file system's metadata and its data structures that the disk was unusable. And this is where journaling comes in mind. So these problems actually come when we're changing the file system's data structures, the inode array, the data block bitmap, the inode bitmap. So when we are actually trying to write those structures, that's when we get a problem. So what journaled file systems do is they actually create a log of all of the changes you want to make to the file system's data structures. And then periodically, they will perform the actions in that log and then clear the log. So the idea is if you get a failure, the log still exists and you can go back and you can redo everything that was in the log just to make sure that you haven't, messed up. Unfortunately, this is not perfect because we might get problems with the logging, but it is significantly better. I've gone from when I was using fat-based file systems and ext2, ext3 non-journal file systems, you'd have to format several times a year. I went to NTFS, which does this okay, but I was still formatting it maybe twice a year. Now I'm using like ext4 and I formatted them when I bought the disk. I haven't had a problem since. I also don't have a lot of power outages, and now I have a big UPS that they sit on. But that's how we handle things today, is with journaling, but it's still not perfect. All right, now there is one problem I want to show you very quickly. Very quickly. So we'll have 2 sample problems in our next episode, and that is file I/O. This is my favorite one. And it's giving you some commands, and we want to know how many reads and writes to the disk are actually going to happen if there is an initially empty cache. So we will let you have a try at that, and we'll take that up in our next episode. Now, that is the end of the file systems module. The quiz, by the way, should be up on Learn. Don't forget to do the quizzes. There will be one more after file systems before your final assessment. The last thing that I want to say is our next episode will actually be our season finale. That is the very end of our episodes. Now, why are we ending with 22 episodes instead of 24? Because traditionally, you would be sitting in a room writing a midterm and sitting in the pack writing a final exam. And we're not doing that, so we didn't have any midterm or final exam review sessions. So that means we are 2 episodes short. So next episode will be our finale episode. So that should be very exciting. And we will cover very briefly these 2 sample problems we introduced today. And we will also talk about virtual machines, because it's a really good wrap up for everything that we've done so far. So I will see you all on Thursday for the end.
Hello, I'm a Mac.
And I'm a PC.
What's with the big hand?
Well, I figured it's time to show the world my position.
Really? Well, that's what I was trying to do with this ultra-hip t-shirt I designed on iLife.
Number 1. Don't want it goofing off.
PC. Such a whiz with those numbers, you know that we can't both be number 1.
I was here first.
That's debatable. Let's not argue about it. I mean, we're the only guys in town. Check us out. Look around, there's nobody else.
You're right. No one else.
No one.
Hi, I'm Linux. And there are an estimated 30 million Linux users out there.
How long have you been standing there?
Long time.
Boy, you sure grew up fast.